Today's a big day. Now, what do we do with this? There's been some suggestions here. Okay, it's always, you recall, going back to chapter 5, we always, when we're factoring, want to see if we can factor out a greatest common factor. In this case, we can. 3. For the number part, we could pull out a 3, and then what's the biggest power of x?
3.
X cubed. 3. So if I undistribute, if I factor out the greatest common factor of 3x cubed, what am I left with?
16. It's not 16.
I don't think so. 24.
24
X to the
right?
6.
Oh.
If I multiply like bases, I add the exponent. So I need to have a 6 there. Good. Plus
5x to the
3. Good. Right.
Plus
I like it.
3x.
3x. No.
Oh yeah, no, just 3.
Just 3.
Just 3.
Just 3 because 3x cubed times 3 is 9x cubed. Right? Right?
Yes.
Okay, because I don't have an x here because I've already got an x cubed. So when I distribute this all the way over to here, I'm just multiplying the numbers. The x cubed is already in place. Okay? All right. Good, good. Okay, what about...
JV and varsity baseball and JV and varsity softball are dismissed today at 2 o'clock. Sorry for the inconvenience.
Okay, what about this? Now, one of the things we can do here that I want to point out, it's a big deal. When we're factoring polynomials like this, what makes this really convenient is that we're able to just look at the number of terms, and that determines the strategy. If we're factoring something with 2 terms, our strategy is factoring pattern. Right? Does it match a factoring pattern? So let's quickly review those factoring patterns. I think, in fact, I'm going to make you memorize these. The one thing we're going to do this week, on Friday, we're going to have a 7.5-minute quiz.
Yes.
Why
Factoring
7.5?
pattern. I just made that.
Oh.
It won't take you very long. It'll be what I'm going to want you. I want you to know. I'll give you a little list of things to know by tomorrow, and it's only going to be like 4 or 5 things. Just some factoring patterns, expansion patterns, very limited. In fact, I will even try to make flashcards for you. How's that sound? Yes. Then you can't do it. Yeah.
What? Where are you going, Freddie?
Okay, so what are our factoring patterns? We got a few of them. Now let's do the squares first. What's a difference of squares? A squared minus b squared factors into what? A plus b times
A minus C.
Very good. Okay. What about a sum of squares? A squared plus b squared.
A plus B times B plus B.
Squared plus A plus
Wrong. If you said anything if you said A or B or anything like that, I know you're wrong because
it's already balanced.
doesn't factor. There is no pattern for a sum of squares. If you have x squared plus something, you're done. It does not factor. Okay? So that's sort of good news. Right? In a way. Less work to do, I suppose. Okay, now what about a difference of cubes? See if we can remember this one. Now, remember this one, there was a small group and a big group. What were the terms? Let's fill in the terms first. I had an A and a B.
A squared.
Just a plain AB for this one. This is still different. Just an AB and a B squared. So the powers all add to 2, right? And then now what about the signs? There are no coefficients in this one. When we're expanding a difference of cubes or a sum of cubes, no numbers show up.
A minus
minus,
plus
plus. And the last one's always positive. Good. So then the last one was a sum of cubes. Same terms, right? A, B, A squared, AB, B squared. What are the signs this time? Okay, good. So which one of those could work for us? And why? Maybe none of them will, and that'll happen sometimes. Okay, it would.
One cubed is one.
Okay, good. The only thing, well now, the 1 could either be a 1 squared or a 1 cubed, right? But this one really only matches a sum of cubes because of the x cubed. X cubed could not really conveniently be expressed as x squared, and even if it could, there's no factoring pattern for that, right? Okay, so the only pattern we have for something plus something is a cubed plus b cubed, and that's what matches the exponent of x anyway, right? So then the question becomes, okay, now that we know that it's a sum of cubes, we've got to figure out a way to write this as something cubed plus something cubed, and then that'll fit our pattern, right? So what's the 1 is what? What cubed? 1. That one's easy. What about the 216x cubed? That's going to be what thing cubed?
216x.
Not 216x. It's got to be the number that when I cube it turns into 216. Which is what? They grow pretty fast. It's a 6. 6 times 6 is 36. Times 6 is 216. So number cube, when you cube things, they grow fast. And by the way, I did put a list, a PDF of, under the Chapter 6 resources, it says list of perfect squares and perfect cubes. You might want to print that out and just have it available. It's got a whole list of all the perfect squares and perfect cubes. You'll need them for this assignment. So does everybody see what's going on then? This is our A, that's our B, right? Now we just follow the pattern. Here's the pattern we're following. So A 6x plus B is 1 times A squared is going to be the quantity 6x squared, right? Minus AB 6x times 1, and then plus B is 1 squared. Right? So what's that going to become if I simplify that? That's going to look like 6x plus 1. Now over here, what is the quantity 6x squared? I've got to square the 6 and the x, right? So that's going to be 36x squared minus 6x times 1 is just 6x. 1 squared is 1. Okay, done. Now we got to check. We got to check and see if we're done, if we can go any further. Obviously, the first one is done because the x is to the first power, so it can't go any further. That one's done. It's linear. This guy here, now you might be thinking to yourself that that looks an awful lot like stuff that we factored in Chapter 5 and hated it, right? Those were hard to factor. The good news is, whenever you apply, remember I mentioned this the other day, but maybe it didn't stick because we weren't actually doing this stuff. Whenever you apply one of these two factoring patterns, the quadratics that you get back will always be done. They're what we call irreducible quadratics. Irreducible quadratic factors, which translates into done. They can't factor any further ever. So that's good news. They're done. So that's our answer. End of story. Okay? Make sense? It is. Factoring takes a while. It does. Math can get long. It's those days are gone. Those days of nice, simple math problems are just kind of out the window now. No, they are. They're just a thing of the past. I don't believe that bit. Okay, so how about this one? What if we have okay, what about that one? Now, which pattern could that match? We got to think about this a little bit. It's going to be, it's a difference, so there's only two possibilities. What would they be?
A cubed minus B cubed.
A cubed minus B cubed or A squared minus B squared. It'd be one of the two, wouldn't it?
It's different in cube.
Yeah, the cube is the one that works. Now, why? Justify your reasoning. How come?
27.
27 is a perfect cube, and so is 125.
Yeah.
What about the x to the sixth? Does that decide for us? Because I could write x to the sixth as what cubed?
Oh, yeah.
Squared, because if I take a power to a power, I multiply the exponents,
Yeah.
right? So I could think of it as being x squared cubed. So that fits our difference of cubes, but I could have also thought of it as being x cubed squared. So the x to the sixth part would have worked either way. It's the numbers that made this fit the difference of cubes pattern, right? Okay? So, oh. All right, so we're going to write that. Now, remind me real quick, what is our difference of cubes pattern? A cubed minus B cubed was what?
A minus B times A squared plus AB plus B squared.
Okay, there's the pattern. 125x to the sixth is going to be what quantity cubed?
5.
5 is the number part, and then x squared. Agreed? Okay, minus what cubed? 3. Okay. So if we follow our pattern then, we get A minus B. Everybody see that?
Yep.
Times, now this is going to be a little weird. We've got A squared, so that's going to be 5x squared, squared, there's my A squared, plus 5x squared times 3, there's my AB, plus 3 squared, there's my B squared. Right? Okay, so 5x squared minus 3 times. What is the quantity 5x squared squared? 25. Okay, good. 25 is the 5 squared. Then x squared squared is x to the 4th. Plus 15 x squared plus 9. Now we got to decide, are we done? Well, this one's done for sure, right? Has to be, because it was the difference of cubes pattern. So that part's done. What about up here? Now this one looks like maybe it could fit a difference of squares, but remember I told you that it doesn't always work. It doesn't work this time, does it? The numbers don't fit. 3 is not a perfect cube, nor is 5. So we're stuck, right? That's it. Okay? Good? All right. Let's try one more of it. Okay, what about that one? Well, it's the only one that could work this time. Because of the variable, we're stuck. It's got to be a cubed minus b cubed, but the problem is 4 is not a perfect cube, nor is 32. Anybody see a possible way out of this? Well, but it can't. Squared won't work because x cubed can't break into something squared. Okay, now factor out a 4. Yeah, I could divide a 4 out of both terms. Factor it out. So if I pull a 4 out of each term, if I undistribute a 4, I'm left with what? Okay, 4 times what is 32? 8. X cubed, and then 4 divided by 4 is 1, right? Now that's better. That does look like a difference of cubes, doesn't it? Right, now that looks like 4 times what cubed minus what cubed? Well, 1 is what? 1 cubed. What about the 8x cubed? What quantity cubed is 8x cubed? 2x. So there's my A, there's my B, right? And so this looks like 4 times A minus B times A squared. Well, what's 2x quantity squared? There's my A squared, right? Plus AB is 2x plus B squared is just 1. Done. Okay. All right, so there's some good examples of polynomials with 2 terms. Well, let's try something different. We got those down, I think. Try like 6. Eventually. Not this year, actually. How about this one? What if we want to factor... Okay, this is the one that I think will be easiest for you because we've already done it this year. What's our strategy for 4 terms? No. Grouping. Factor by grouping. So we're going to always break it into 2 groups of 2 added together.
Yeah.
Okay, and then what do we do to the first group?
Take out x cubed.
Okay, take out the greatest common factor,
X
which would be an x squared, leaving us with what?
X plus 3.
Okay, x squared times x would be x cubed. X squared times 3 is 3x squared. Good. Okay, now here's the part that's tricky. You got to be very careful. You can make this easy.
Just put an x plus 3 on the side.
Good. So over here, we know that this thing, if it's going to work, and we don't know that it will, it might not. If it is going to work, we know that this has to be an x plus 3. Has to. So the question then, all you have to decide is there something that could go out front? Could I factor out or undistribute something that would make that work? And here's the way you can do it. The easiest way would just be to say, what times x is 10x? 10. Now the question is, does it work for the 3? 10 times 3? Yeah, it works. Okay, so this one did factor by grouping. They won't all. Okay. So then all we've got to do now is we've got these 2 terms. Each of them has an x plus 3, so let's pull that out front. Leaving me with what?
X squared plus 10.
Good. Okay, are we done? Why is this one done?
Sorry.
Is that right? Okay, now why is this one done?
It's just a single x.
Yeah, it's to the first power, right? Done. What about this one? It's got an x squared. Is it done? Could I break that down further? Because it's got an x squared in it. The answer is no. I know for sure no. How come? Well, even if it were, it's x squared plus 10. There is no pattern for for sum of squares. A squared plus b squared doesn't exist, right? So because of that plus sign, we're done, right? Because that's a plus, done. Right?
Wait, are you factoring by x squared?
Well, we factored by grouping, so we took the greatest common factor out of the first group, which was an x squared, leaving us with an x plus 3. That means from the second group, we would have to have the same leftover factor.
Okay.
Does it work? Yeah, if we take a 10 out, it does work. Okay? Okay, one more of those, how about? Let's try this guy. Okay, now be careful with these. Don't just jump into the pool until you know that the water's not boiling or something. You gotta analyze the situation a little bit. What's that?
Like a labor hospital.
There you go.
You can't take anything out, so you.
Okay, yeah, the question is, can we always want to, before we start factoring, can we pull out a greatest common factor? It's always a good idea. Is there something, no number, right? But is there a power of x that I can take away from each one? X. The 1, right? I can take an x out of each term. So if I factor out an x all the way out, then I'm left with what? 3x cubed, sorry, 3x cubed, you're right. Plus 9x squared, and that's going to be our first group, isn't it? Plus, okay, agreed? Okay, now here's an important thing to know about. When you're factoring, when I pull that x out, notice that the x is outside of the square brackets. This is a good idea to do. When you nest a bunch of parentheses like this, if you have parentheses here, then next to those put brackets, so it's easier to tell which level you're on, right? Brackets go with brackets, parentheses go with parentheses. So then that means that because the x is outside of the brackets, everything inside of the brackets is in its own little universe. We're going to work on that stuff by itself. We don't even have to worry about the x for now, because it's outside, right? We're working inside the brackets only. So inside the brackets, yes. So inside the brackets, in that first group, what's the greatest common factor? 3x squared. Okay, leaving me with, from the first group, what?
X plus.
Okay, 3x squared times x is 3x cubed. Plus what? What would go there? 3. Okay, good. Now, we just know that over here, we're going to have to get an x plus 3.
That's just a 1.
Can we do it? Well, yeah, that's what we started with, right? So what's out front then? What would we distribute to this? Okay. Now, this is important, though. This is the most common mistake people make with factoring by grouping is they forget that that 1 is there, right? It is there. Now, when I take out the x plus 3, look what we get. I've got this x already out front. If I pull an x plus 3 out front, what am I left with? I'm left with 3x squared plus what? 1. The 1 is there. If you didn't realize it was there, you would have just said 3x squared, which would have been wrong. Because when you divided x plus 3 away, well, x plus 3 divided by x plus 3 is 1. There's a 1 left behind. Right? Does that make sense? That part is the most common mistake, guaranteed. Every year, that's the one I see the most. And so there's the fully factored polynomial. Can we go any further? X is done. X plus 3 is done. What about this guy?
It's positive.
It's a plus sign, x squared plus, so it's done. Right? How about that? Okay? All right, last one. And then this is it for, if you get this, you get it all. Yeah.
If you don't get it.
And then you don't get it all. No. Okay, now with this one, I got to have absolute attention. If I can get your undivided, focused attention, I can guarantee everybody will understand this. And this is the one that you could have trouble with. This looks, would you agree, this looks an awful lot like something that we might have done in chapter 5, only we didn't have x to the 4th and x squared. In chapter 5, this would have looked instead maybe like, how about like this? It would have looked something like, oh, let's call it y instead of x. Let's call it y squared plus 3y plus 2, right? That's no big deal. Those were the easy kind to factor in chapter 5 because the number in front of x squared or y squared in this case, a, was equal to 1. So remember what we said was if these things broke apart, if they factored, I'm just unfoiling it, right? And first times first has to equal y squared. So they're both y's. That part I know. The question is just, can I find magic numbers? The numbers would have to multiply to, no, to 2 and add to 3. So what two numbers are those? 2 and 1. Aha. So plus 2 and plus 1. I'm done, right? Okay, now this is different though. This is different than what we're doing over here in chapter 6. But I want you to notice that the pattern is the same. If I thought of this problem over here, this x to the 4th plus 3x squared plus 2, if I thought about that in pieces of x squared instead of just plain old x's, look what happens. This becomes x squared, right? X to the 4th is just x squared, plus 3 times x squared plus 2, right? Now, you don't have to do this, but this is actually something that we do a lot in algebra. We could do a variable substitution if we wanted to. We could say, okay, let's let every place we have an x squared, let's set that equal to y instead, right? Just to make things look easier. Then wouldn't this become the same thing that we had over here? Y squared plus 3y plus 2, right? Which we already did. There's our answer. That factors into y plus 2 times y plus 1. But those actually aren't y's, are they, after all? They're x squareds. We called them, we just made them look like y's. We made that change just to make things look simple. But in the end, we really want our answer in terms of x's, right? So we could take those y's and flip them back to x squareds, right? So the y's become x squareds, and we end up with x squared plus 2 times x squared plus 1, right? Looky there. And are we done? Do those go any further? No, because I've got pluses. Now, I would argue that you don't have to do that switcheroo. You could really just go straight from there down to there, couldn't you?
Yeah.
Once you break this thing up into things that match the quadratic pattern, even if they're not plain old x's, they might be x squareds or even x cubes or something, right? Once I get it into that quadratic pattern of something squared plus a number times something plus a number, right? A is just 1, so I get 1 times something squared plus b times something plus c. That's quadratic. And it might factor in the same easy way that it did in chapter 5. Okay, let's try one more of those, and we're done. How about this guy? What about that? Now that's a 4th degree polynomial, sure, but can I break that up so it looks like a quadratic pattern? Right? Can I break that up so it looks like something squared plus that something that looks like it's 0? Let me change that. Go away. Oh, whoops. So it looks like something squared plus 10 times something plus 16. That would be quadratic. If those were x's, that'd be a chapter 5 problem. In this case, they're not x's, they're x squareds, right? Because x squared is x to the 4th, and then that's just 10x squared, right? But there's the pattern, right? There's the pattern. So this might break apart now. if this breaks apart, if I unfoil it, well, first times first has to equal x squared squared. So those are just x squareds, right? Now, what would the magic numbers be that multiply to 16 and add to 10? 8, 2. How about that? So we got it, right? It's just matching that pattern. I lied to you. Let's do one more. We can do this one. You literally, this is the hardest one. Oh, yeah. Okay, you're right. I'll stop there.